Ja, ist so einfach.
If you don't mind, we'll give the chair another 2 minutes, and otherwise I will start.
Sorry, it took me a long time to fly from Moreira to Paris. It is not close. Sorry, I was lost. Okay, sorry guys for being a bit late. First of all, are you all ready to go?
Yes,
ready?
yes, I'm ready.
You all started it, right? Thanks for waiting for me. Look, thanks very much for joining. So it's my pleasure to welcome to the afternoon session, session 2F, where we have a number of presentations, and we will start with Professor Maia, please. Thank you very much.
Thank you for
Welcome, and we know the format: 15 minutes plus couple of minutes questions. Thanks.
I will talk a little bit about master curve evaluation at elevated loading rates. So the topic is ductile brittle transition at elevated loading rates. So first I will start with overview of the standards for fracture mechanics at elevated loading rates and describe some projects we had in the past on this topic, and then we will deal with the results from fracture toughness tests on two different materials, one very homogeneous from a not used RPD material, and another one from a standard high strength quenched and tempered steel plate. So in Annex 1 of ASTM E1921, which is the master curve method standard, are special requirements for determining the reference temperature at elevated loading rates described. And the tests itself are performed using the Annex 14 of ASTM 1820 for larger specimen, and for the pre-cracked P.M.G.P specimen there is a special Annex A70. There exist a lot of results for the small pre-cracked P.M.G.P specimens, but not for larger specimens like 1-inch CT. And so we had these projects, and we started with very high loading rates, 10 to the 5th megapascal square root meter per second, and we had published a lot of results from these. And now we go to lower rates and look if at intermediate loading rates we will get similar results. This is a result from a previous project. You can see the master curve and the experimental data in the region near the reference temperature, and what can be seen is that at high test temperatures the results are deviate from the expected distribution for this test temperature, and so we get different results if we test at higher temperatures, much lower reference temperature like -12 degrees Celsius for -20, for +20 degrees, and for minus we have the result of 50, and this is a large difference, and there is known some reasons for that. One is that at very high loading rates you have temperature increase at the crack tip from the dissipation of the energy from the pacification. And this means that the effective temperature near the crack tip is a little bit higher, and this shifts the result. But the other thing is we found that we have local crack arrest found on the fracture surfaces, and this is the second reason for this deviation from quasi-static behavior. So this is the material we use. It's equivalent to the 508 grade 2, and it was very homogeneous. And we, in addition, we took the specimens from a definite thickness between 2/3 and 3/4. The quasi-static reference temperature was -68, and RT-NET is -20 degrees Celsius. And these are the results for a lower rate. 10 to the third is not so very fast. So it's only for a 1T CT specimen, it's about 20 millimeters per second. So you can use standard clip gauges for measuring the COD. For the 10 to the 5th, you have to do optical measurement. And here you can use standard if you have the correct bandwidth for your measurement equipment. And what you can see, the effect is smaller than for the 10 to the 5th, but we made a lot of tests, 30 tests at +20, and you see there is a shift of 10 degrees Celsius still, even if we don't expect much temperature increase at the crack tip. And we can show this in the distribution. If you take the probability from the standard VIVO used in the 1921, you can linearize the results over K. And what you see is that the distribution is different from the solid line, and we have less results with low K, especially for the red one, the red curve, which is 0 degrees Celsius test temperature. And this seems that the K min, which is assumed in 1921, is too low. And this is the same as that there is something which arrested tests which wanted to initiate. And this is the same for 10 to 400. So still you can see an influence for higher test temperatures, a shift of also 10 degrees Celsius for the result. And here we have the most tests at -20 degrees, and also there the fit doesn't fit to the solid line, which is from the standard distribution. And the effect is increasing if we go to 10 to the 4th, and 10 to the 4th is the rate where the temperature increase at the crack tip starts to grow. So we have both effects, crack arrest and the temperature increase. So these are the analysis of the probability for 10 to the 4th. This is an example what you can see on the fracture surface of these specimens. We have the pre-cracking of the lower bottom and then the stretch zone. And what you can see is that in this region, we have in the ductile crack growth, we have some, this is an enlargement, we have some brittle fracture which stops here. And this is, we call local arrest, because it's only, the whole diameter is 100 to 200 microns. So it cannot be seen in the global FCOD. So this is the overview of all the results I showed you. And So the result is it would be better to take a higher K-min if you want to describe this distribution correct, or you test only near the expected reference temperature. And then we looked if there is an influence of the material, and this is the plate of the S690 high strength material. This is the position where we took the specimens from, and what you can see here for 10 to the third, it looks very different. And we have no influence even for 10 to the fourth. We only have influence if we go really far, and this is too far for the evaluation because there is this plus minus 50 degree validity criterion. This distribution looks nevertheless suspicious. So we looked if there's a difference in these two layers we get the specimens from. And so we found that the layer A is very different from the layer B. So it was 1/4 and 3/4, and we hope it's the same, but the homogeneity is not good enough. And so this influences also the overall result of the shape of the master curve. But if you fulfill the requirement of the plus minus 50 degrees, you have no influence on the shape. And this is the result if you only take these two temperatures for 10 to the fourth. And this is the overview of the different results. What you can see is this is quasi-static, and we have only a small difference of 7 degrees in the reference temperature, but it's increasing with the loading rate. So if you have only small inhomogeneity for quasi-static tests, maybe it will increase with the loading rate. So these are the separate evaluations of it, and there we have a large difference between the two layers in the results for all loading rates. So I come to the conclusion. The use of the master curve method at elevated loading rates, according to the Annex 1 of 1921, in the ductile brittle transition region has some limitation, but this limitation depends on the material and on the loading rate. For very high loading rates, it's larger, the influence, and for test temperatures near the crack arrest temperature, the influence is larger, because for the S690, the results were very low temperatures, and the arrest temperature was nearly the same as for the upper B material. So this might be the reason that we also found only a few of these local arrest, which we've and not so many as for the other material. And so there's a shift in the distribution which could be compensated by changing the K-min, but the recommendation is that you test near the reference temperature, because then you minimize additional uncertainty in your measurement. Thank you.
Thank you so much. Thank you, Mr. for a very interesting presentation. We have time for maybe 1 or 2 questions from the floor. Anyone? Yes, please.
One question. What type of test machines did you use for the high loading rates?
Servo hydraulic machine. And up to 10 to the 4th, we take the force measurement from the piezo quartz at the machine, and for higher temperatures, we make an instrumentation with strain gauges directly on the specimen.
Okay, thank you.
And this, sorry, the thermocouples are well calibrated?
The thermocouples are positioned near the crack tip, yeah.
Okay, so it measures the temperature.
Get temperature on the spectrum.
Okay. Any other question? If not, let us thank Professor Maia. Thank you very much. Thank you. Our next presenter is an industrial approach. The next title is an industrial approach to high strain rate testing. And it says here video. So we will have a video being played, is that right? So it is interesting hybrid mode, face to face and video. Is it a live or recorded? I'm not sure.
I think it is recorded.
Okay, that's fine.
Everyone, welcome to this European Conference on Fracture. Analysis of this great conference for the opportunity of implementing in this great gathering. My name is Emilia Chamaka. Yes, today I'm not saying this.
So we start from the beginning. Okay, so we have the video. And so we have the video presentation to be presented by Emily Charnaka Ikene Uzudai. So we welcome her virtually to our conference. Let's start.
Hello everyone and welcome to this 23rd European Conference on Fracture. Thank you organizers of this great conference for the opportunity of giving me to speak today in this great gathering. My name is Emilia Chamaka Ikene, PhD student at Lancaster University at TWIE Modern Institute, National Structural Integrity Research Center, Cambridge, United Kingdom. Today, I will be going through an industrial approach to high strain rate testing, and I'll be talking you through this topic today in this great conference. Co-authors are also on the screen, Eugene, Drew, Wayne, and Maris. I hope you enjoy the rest of my presentation today. We'll be showing the abstract of this conference, which I will not be reading through. This abstract is contained in the program of the day. And we're talking about some of the approaches we applied in Australia to measure high strain rate testing. Nowadays, we have used some methods like instrumented P.M.G.P testing, the impact testing, the servo hydraulic testing machine to be able to measure high strain rates loading test. We also applied some computational analysis and also the analytical model to also analyze some of the results. We went ahead to use the artificial intelligence for this. Start by showing some of the examples, the experimental setup which we have utilized in this project. Here we can see that we have the hydraulic machine. You can see the flat SI specimen on it, speckle patterns around it. This is used to be able to utilize the camera and it's captured for the digital image correlation analysis. Also have the 3-point bend specimen here, which we use for the trapeters and also for the impact testing. These are used in order to obtain numerical properties at high strain rates, such as fracture toughness and then the ultimate tensile stress. Utilize the digital image correlation to analyze the results which we gathered from the experiment. Since it's difficult to use the traditional approach for strain gauge to measure the strain in this experiment. So we utilize the speckle patterns and then camera, analyze it in the GM software to obtain the strain. And you can see in this video how the material started and then up to fracture. So this material propagated and then fractured. And on the here we see the curve which we have obtained using the data points from the GOM machine, and then from there apply force. We utilize the approach of thermal dilatation to be able to measure the ultimate tensile strength. Since there is a little much difficulty in obtaining the ultimate tensile strength in this material, so this thermal dilatation distance was calculated. This is the thermal elasticity of this material. The material we are using is the X65 grade steel, 0.1% carbon content. So this thermal elasticity value is assumed to be 18.8, and then we have test duration for the whole test. For the static ones, we have a higher test time, and then the highest displacement rate 5.4 up to 15 meters per second. We have the thermal dilatation distance, that is the higher the strain rate is going, the lower the thermal dilatation distance. And because this thermal dilatation distance is recorded as short interval, this high strain rate is considered as adiabatic process. You can see on this slide four different strain rates which is applied. And the static one here determine the elasticity up to 200, and it continues all through the experiment, such that the ultimate tensile strength is obtained later during the experiment. But for the case of the high strain rate, we see that the ultimate tensile strength is reached at the first part of the test, and before thermal softening is in the material due to the increase in temperature. And this has made us measure the ultimate tensile strength at the beginning of the experiment, after which there is an increase in the stress applied. Then there is increase in the ductility up to 3 times that of the strain rate. Here we can see the different mechanical properties obtained beyond modulus, which is about 207 to 210 for the quasi-static testing. For the dynamic one, we have to range from 240 to 460 depending on the strain rate. The 0.2 proof strength is also increased from, we have the 640 to 688 in dynamic one, and about 480 to 500 in the quasi-static one. The ultimate tensile stress too is also higher, it is about 740 to 855 in the dynamic one, and then lower, about 600 in the quasi-static one. So we can also see the increased elongation in the dynamic one, because it's higher due to the fact that we have a higher temperature, which decreases the elongation or decreases the strength of the material. We went ahead to utilize the analytical model to model the plastic information of this, and we utilized 3 of these models. So the first one we use is the Johnson-Cook model, which the equation is given here, the flow stress. The constant parameters are determined from experiments using different approaches. We use the reference strain here as 8.2 to 10 to minus 5 for the strain rate. From the experiment, we derive the parameters for A, B, N, the C, and M constant. We only concentrated on the room temperature and didn't use any other temperature for this one. You can see the graph here, it shows good correlation with the experiment, then the Johnson-Cook model calculation. We also utilize the dislocation evolution model, which we have the flow stress and the density, dislocation density. So the equation here embedded the photo drag effects here in this equation, which is the first part of this equation. And then we have different values for alpha, and for this material it ranges from 0.05 to 0.6. And we can see also for the different strain rates here, the graphs related very well as they propagate. The third one we utilize for the analytical model is that of the cosmetic formulation ECE model, because the material we are using is the X5 ratio, and it's a BCC, the body centered material. So we use the dislocation storage coefficient A1 here, and then the dynamic recovery coefficient FEC here. So with this equation, we obtain the flow stress that we are undergoing at different strain interval. The three analytical model in correlation with the experimental value are shown at different strain rates here, which we use different force strain rates here, and we see there's a good correlation for the three models and the experimental. We went ahead to use the final element analysis for these high strain rates, how the hammer is dropped at different velocity, and then we have recording. See how this propagates. We see that the hammer dropped from a distance, so it's getting contact with this specimen. Then it continues until fracture propagates. I will forget to mention that we utilize different notch, which is about the 5-meter notch and also the 2-meter notch, as we see in this simulation. Another approach we use is the artificial intelligence method. We apply the machine learning algorithm using some features from the experiment. Here we utilize the crack length, and the crack length, which was rated using EDM notch. So we have different values for EDM notch, and also we have the pre-crack ones, which was done using particular pre-crack method to induce the crack in the experiment. The applied force are for different experiments as well, and then the KQ for the materials which we are using. Also, because we are trying to predict the fracture toughness, so this shows the facial matrix for the features which we have used, and we can see that it has good relationship, except for the pre-cracked one, which has some lower value, due to the fact that some of the materials are pre-cracked, while some are not pre-cracked. So we proceed to use this to predict the toughness, and we have here the result which we have obtained from the algorithm, and we could see the true toughness, which is on the x-axis, and the predicted toughness on the y-axis. From this, we could say that there is an agreement with this, and then it is sufficient to utilize the machine learning to propagate, to predict the fracture toughness material. Conclusion, we've seen how different methods has been applied to measure high strain rate testing, using the CHAPI, using the Istrom machine, and also we have also applied the high-speed camera in digital image correlation to obtain the strain in the material, and then be able to obtain our strain curve using the point data which we have obtained from this method. The analytical model was applied to, and also the computational method, as well as the artificial intelligence method. These are used for predicting, and then we correlated the experimental results with them, and we could agree that there is a quite reasonable correlation between these methods and that of the experiment, and that is to say we could predict using this method the fracture toughness of material at different conditions. The last point here is the limitation we experienced during the use of machine learning. We have here the data, because we have limited number of data for this. based on the fact that they come from experiments. So it's very expensive to run some of these experiments, and we couldn't get as much data as possible. We hope to add more experiments and then more data to be able to enhance this model and make the prediction accuracy better. So thank you for listening to my presentation today. And we have our contact details on the screen there in case anyone wants to reach us for any question. We are very happy to answer any question. And we thank our sponsor, the Red Register Foundation, for the support they've given us all through and the provision of materials. I won't forget to thank the organizers of this conference once again. And then I hope everyone enjoys the rest of the conference. Thank you.
Thank you very much. Unfortunately, I don't think we can do question answer, which is a disadvantage. So we should go to the next presentation, right? Yeah. Okay. Next presentation is in person, face to face. Its title is paper number 422, Structural Integrity Assessment of a Spent Nuclear Fuel Transportation Cost under Aircraft Engine Crash. Is the presenter here? Paper number 422.
No presentation.
We don't have
The presentation.
Okay, presentation is missing. Presenter is missing. So according to the rules, we go to the next one, right? The next one is presenter there, 437.
It's me.
Missing?
It's me.
Oh, it's you. Okay, you are there. Okay, that's fine. Great. You are hiding. Okay. Okay, welcome. You can present. Good, great. So your talk is passive safety solutions on coach, according ECE R29 experimental and numerical analysis, right? And you are Rodrigo? Okay, welcome.
Thank you very much for your kind introduction. So my name is Rogério Lopes, and today I'm playing at home. I'm from Portugal. At the moment I'm working at ECE. Today I'm going to talk about passive safety solutions applied on coach. That is in the scope of my PhD thesis. I'm a PhD candidate. I would like to welcome the audience and thank you the team. So in this slide you have a short introduction to what I'm going to talk about. I will start with the motivation, what motivates us to spend time working in this project, and afterwards I will introduce some work that is already performed by another author so far. Then I can advance that we are testing Regulation 29, so I'm going to explain the experimental procedure. Experimental procedure and the numerical methods that were employed in this project. I will discuss the results and then I will finalize with some remarks and conclusions and the future work as well. So nowadays, transportation plays an essential role in the society. There are a lot of people that use transportation, a lot of transport, different kinds of transport. So it's necessary to ensure the safety in that transport. How can we ensure that safety? Basically, by testing the structures. The key objective of this project is to provide innovative safety solutions applied on coach. I don't know if you know, but a coach is a tourism bus. Our main goal is the development of a new generation of safer bus, basically. We are studying a coach, just a section coach, and we are going to employ the Regulation 29 to see if it is according and it is safe. I can advance that at the moment the current chassis are insufficient to absorb all the released energy involved in a collision, in a frontal collision. This results in the driver invasion, or the driver area invasion, and maybe sometimes depends on the velocity, the passenger's area as well. This is why, because at the moment there is no regulation to certificate these vehicles. The manufacturers don't have a rule to follow to certificate their vehicles. But there is one regulation that is applied to a truck with separated cab. This regulation is named by the regulation 29, and it certificates the vehicle in case of frontal collision, but is applied just to trucks with separated cabs. As this is an investigation project, we are going to adapt this regulation to our case. We are employing several experimental methods to monitor the structure, and we are going to employ as well numerical methods. The numerical simulation used in this project was performed by Pump Crash. At the end, we are going to conclude if it is according to norm. So, I can introduce the regulation, explain you what is this regulation. I have a short video there, just to you better understand what is this regulation. So, basically the vehicle is totally immobilized, and the striker with normalized dimension will strike the front of the vehicle at a specific energy. It depends on the category of the vehicle. The pendulum should, in our case, should transfer the vehicle at more or less 55 kilojoules of energy. Okay. So far, there is some work that can be found in the literature, but they are very superficial and mainly of numerical nature. Some of the authors studied the approach like mine, and they concluded that was not according to the norm. So they proposed three optimized models in order to be according to the regulation. By introduction of sources or attenuators in order to better control the absorption of the kinetic energy. At 2020, there is a work where the author employed experimental methods. He developed a striker and he uses frontal chassis, but just the chassis without outer panels, windshields or dashboards. They didn't use monitoring technology like strain gauge or digital image correlation. He performed as well numerical methods, but he validated the model by comparing the displacement of the steering wheel, by comparing visually. So far, Mercedes-Benz claims that his model, Citaro model, is according to the norm. But Citaro model is a urban bus, not a tourism bus. Moving on to our case, we are investigation. This section is a M3 class vehicle, and this is a replica of a Scania. In order to reduce the expenses, we are just testing the frontal section. We replace the tires and the suspension system by a rigid chassis directly connected to the ground floor, by 6 pins. As well, the entrance was replaced by 2 beams. This can help us understand how the door influences the safety. And so, to perform the test, it is necessary to develop a striker, an impactor, and our impactor weighs 2,500 kilos and will transfer the section more or less 55 kilojoules of energy. It's necessary as well to develop a quick release system to release the pendulum instantaneously. The quick release system is based on a hydraulic actuator. When activated, the pin retracts and the pendulum falls. Regarding the monitoring system, we are using 15 strain gauge displaced in the structure. 2 accelerometers is as well placed in the front of the vehicle, and the driver side of the lateral side of the driver side is also monitored using digital image correlation. This is the camera to acquire the video recording. Regarding the numerical procedure, like I said, it was performed in pump crash. A lot of formulation are employed since we have different type of elements, type of materials, a lot of parts. The simulation is dynamic explicit with mass scaling. Regarding the materials, I have a quick summary. We have different materials like 2 alloy steels, 1 alloy aluminum alloy. The outer panels are made of composite, is polyester with fiberglass. The dashboard is as well in composite, plywood to the floor. The seat is made of foam. It's a very complex model. And here I can show you the first look.
Maybe it's the impact. Bro.
I'm sorry. So here I can show you the first results. This is merely a comparison between the video recording, between the FEM result and the experimental result. And as you can see, the geometrical deformation is quite good. From the other side, as this side has lower stiffness, there is some torsion of the pendulum. Particular behavior happens in this pillar. This calls buckling, but it keeps very good as well. Regarding the DIC data, here I can show you the results of the displacement along the x-axis. At the first sight it looks very different, but no. This is because of the crashing area that masks all the contour field. If we look at this node, the displacement of this node, it retracts almost 50 millimeters, and 50 millimeters in the experimental test correspond to the green color. It's almost there. In the vertical side, and the crushing area has lower influence, the contour field has higher, better correlation. So the last result is regarding the strain gauge. Like I said, we placed 15 strain gauge, but in this presentation I just show you 5 of them. Those that were placed in the A pillars, this one, and it has more or less a good correlation. Better correlation is observed in those that were placed in the ceiling, and this is a particular that returned bad results. Maybe due to the near approximation, to be near of the impacting area, maybe the glue failed or something happened and it returned in wrong value. But if you look at these values, we can validate the numerical model. So, in order to conclude, we are studying M3 vehicles according to Regulation 29 that tests the vehicle to a frontal collision. We performed numerical tests and experimental tests, and we observed that there is a high resemblance between experimental and the FEM. Okay, a good agreement between big data and FEM data. There was a clear visualization of the impactor torsion that was very difficult to achieve in FEM simulation. Okay, I forget to mention something important. How can we validate the structure? We have a mannequin. We have a mannequin with normalized dimensions that after performing the test we should introduce the mannequin into the driver's seat. If the mannequin does not touch in any component, so it's according to norm. In our case, we introduced the mannequin into the driver's seat, and actually it did not touch in any component, although during the impact we observed that the dashboard would injure the driver. So we cannot validate this structure, basically. According to the norm, is valid, but there is a but. To future work, there is a need to improve the position of the dashboard. We are going to perform new dynamic tests by the inclusion of the passenger side door. I think it's important to monitor the driver area, the residual space. We are studying internally to replace the composites, the outer panel made of composite, to DCPD polymer. This is a polymer highly used in the automotive industry. According to the results, we are going to investigate the possible structural changes in order to optimize the structures. And I would like to acknowledge the project. Thank you very much for your attention. If you have questions, feel free.
Thank you for a very real-life study with experiments, with numerics. Any questions? Yes. No question from the floor? Yes.
The high strain data for your simulation, did you this by your own or did you get it from anyone else?
So far, the mechanical behavior of the materials, right?
Yes.
So far we use a typical static read data, but we are also studying internally to perform high-strain tests to obtain the mechanical behavior of the material when subjected to high-strain rate.
Yeah.
Yes.
But these data should be available also from the vendors.
Like those who make the bus song. They should do some tests.
That's a good question. Thank you.
Any other question, please?
Thank you, Mr. Chairman. Rogério, what you told that the dummy, the mannequin, did not touch all the driving environment. Was he or it using a seatbelt, or it was simply
No.
set at the driving position?
We have to just to sit the mannequin in the driving position without seatbelt, or I forget something is important to mention. The seat must be in the most retracted position. If we have an accident, the seat sometimes it retracts. So the mannequin should be introduced in the retracted position of the seat.
Just a question, you had some data last slide, not the last slide, the last slide. Last but one slide, you had some comparison.
Sorry. Last?
Yeah, this one. So this one, what is plotted on y-axis? Strain, right?
This is time and this is micro strain.
Okay.
Yes, you are right. It's difficult to read.
Yeah, okay. So, but did you you have an accelerometer? So you could have compared the acceleration of your numerics, and that's the easy way, because strain could be difficult to correlate in this case, dynamic cases.
We have the acceleration data, but so far I have no time to treat the data.
Okay, understood.
I have the data with a lot of noise and a lot of.
It will not look good here.
Yes,
It's good.
it's not possible to have a correlation.
Process it.
Yeah.
That's fine. Look, that's great. Great presentation. Any other question? If not, please join in thanking Rodrigues for an excellent presentation. Our next presenter is here, Fred. Okay, and so Sebastian Hansha. So Sebastian will be talking on one-step dynamic calibration of strain measurement in a split Hopkinson pressure bar, which is also again the high strain related work. So we should be it will be interesting topic to watch again. Please, we are welcome to start.
Thank you, Mr. Chairman, for this introduction. As you can see, I want to talk about Hopkinson pressure bar. And first, I'll give you some outline of this talk. I'll give you a motivation to this short investigation. We'll also give you details of the methods and the materials. We'll show you and discuss the results. And of course, I will summarize my talk and give some conclusions. So, as you may know, split Hopkinson pressure bar, or also named Kolsky bar, is used for high strain rate testing, for example, for compression tests. There are long bars, or slender bars. These deform elastically, and the elastic deformation should be evaluated and by using strain gauges. And these strain gauges need to be calibrated, and we do it in a dynamic way. We introduce a known pressure pulse, and then we assume a conservation of momentum, and then we can make the dynamic calibration. I will show you in the next slides how this works. But rearrangement of the bars is necessary to perform the dynamic calibration. So the aim of the investigation was to make a calibration in one step without rearranging the bars, and maybe also to recheck the calibration during actual tests. And another thing was to use any kind of pulse which is introduced by the striker bar. So let's have a look at the drawing of this Kolsky bar setup. We have the striker bar, which is propelled by compressed air. The velocity of the striker is measured by two light barriers. One of them is used as a trigger for the data acquisition system. The striker bar hits an incident bar, and between the incident bar and the transmitted bar there is a specimen, in this case a compressive specimen. Then we also have an optical extensometer, which measures the displacement of these two interfaces, 1 and 2. Let's have a deeper look. To measure the displacement here with this optical extensometer, we put some stickers on the bars with black and white edges. Why are these interfaces are moving? Because there are the pressure pulses. The striker bar introduces a pressure pulse. This is called the incident pulse going through the incident bar, and this pulse is partially reflected to a reflected pulse. This is a tensor pulse, and partially transmitted in the transmitted bar. And so we have two displacements, U1 and U2. And of course, if we perform a compressive test, U1 is larger than U2. So what do we measure? We measure a voltage of the strain gauges, which are applied on the surface of the bars, and we measure displacement by the optical excimer. What do we do with this measured characteristics? We calculate the strain by using a constant which incorporates the characteristics of the strain gauges and the gain of the amplifier and so on. And this one has to be identified. And from the strains, we can calculate the forces and also the displacements. And here you can also find this constant. And so you can use the integral over time of the measured voltage. So a normal calibration looks like that. We perform a so-called bars apart calibration. We have to know the sound velocity of the bars. We have to measure the velocity of the striker, and we have to measure the maximum voltage of the incident bar. And from this measurements we can calculate this calibration constant, and then we have to rearrange the bars. Then we have to perform also again bars apart with this with the transmission bar or transmitted bar. We have also measure again this these things here, rearrange, and then we put the bars together, and we have to measure the strains in the bars with these calibration factors, and we have to calculate a transmission factor, and then we can perform an actual test. So with the proposed method, we just measure the voltages at the bars, the incident bar, the incident pulse, the reflected pulse, and the transmitted pulse, and we measure the displacements at the two interfaces, and from this measurement we directly calculate K1 and K2, the two calibration factors, and then we can perform a test, or as you will see, we can also use an actual test to calibrate the test. For the material, we use high strength quenched and tempered steel with the characteristics shown here. So let's go to the results. First, we perform the tests without a specimen and no pulse shaping. That means the incident pulse is quite rectangular. There is no reflected pulse, and also the transmitted pulse is also quite rectangular with some dispersed effects. And we measured the displacement of the interface 1 and displacement of the interface 2. From these measurements, we can generate a new diagram. Here's the measured displacement of the interfaces, and on the x-axis there is the integral of the voltage over time. And then we can see a quite linear relationship, and we can calculate the slope of this linear relationship. And here you can see what was assumed. We assumed that the optically measured displacement is of course equal to the calculated displacement of the strain gauges, and this is the actual equation here, and this K factor was calculated. So this is basically the dynamic calibration here without a pulse shaper. In the next slide, we use a pulse shaper, a quite thick pulse shaper, which generates a quite long rise time of the incident pulse, which of course much lower the dispersion effects. We also measured the displacement here, and then we can also have a look at the measured displacement and the calculated displacement, and we get the same slope, also with the same equation here. So then we performed an actual test with the known calibration constants. We also use a smaller pulse shaper. We introduce this incident pulse. When we use a specimen, we of course get a reflected pulse and the transmitted pulse in red. And then we can compare the displacements measured by the optical extensometer, and the calculated displacements with the known calibration factors. And they look pretty much the same. And this also means that we can use the data of an actual test to calibrate the test itself. The calibration really was performed before the test, but if we did not know this case, the K1 and the K2, we would get it from the actual test. So, let's summarize my talk. The most important thing I think is we have a consistency here regarding conservation of momentum. During a classic dynamic calibration, you assume the conservation of momentum for the bars apart calibration, but you assume that there is no conservation of momentum during bars together calibration part. But in this method I presented here, there are no assumptions at all. We just compare measured signals. Then there's, when you have an optical extensometer, you need only one step for the calibration. You do not have to rearrange the bars. And it's also possible to perform the calibration during an actual test. And another thing is you can check the calibration each time you perform a test. So maybe you can check if the instrumentation of the bars is still intact. You can detect a degradation of the instrumentation. So thank you for your attention. Thank you. Thanks for the financial support, and open for questions.
Thank you very much. Any question from the audience? Yes?
Yeah, I have a question. You use your optical extensometer for the calibration, and my question is, how do you calibrate this extensometer, and do you use a dynamic calibration or a static one?
The only thing is to put the extensometer on the right position, so that there is a right angle between the bars and the extensometer.
Yeah, that's clear. But from a quality management point of view, you have a reference. You have to have a reference for the extensometer.
Yeah,
and this is not easy to find a reference with a dynamic calibration for this, because it's all relying on the quality of the extensometer.
Yeah, the extensometer was calibrated on a static way to with known distances, but it was not. This extensometer was not calibrated in a dynamical way. But I think this extensometer, it's extensometer of Rudolph, or formerly Zimmer. I think this works for the static test, but also for the
and it should be fast enough for.
Yeah, of course, fast enough. Yeah, please.
I have a couple of questions, probably due to the fact that the presentation is quite fast, so it's sometimes difficult to capture some details. But I have two questions. One is, when you calibrate, when you do the dynamic calibration with the two bars, in your case, are the bars same cross-section, same materials, or they can be different cross-section or different density or mechanical units?
In our case, the bars are identical, so same diameter, same material, but this is no. I do not assume that this is the case. I think we can also do this calibration with different bars.
Because I think
I
it's
just measure the
because of displacement based, so you just calibrate the displacement from the test and.
I could just compare two differently measured displacements.
And so you, for the transmitted bar, if there are different mechanical impedance, you are assuming that the impedance matching all the pulses transmitted, right? Because if there is reflection, then the displacement at the incident bar is reflected minus intensity divided by rho c.
This is Yeah. This formula is a little bit simplified here. I use the for calculating the displacement at the incident bar. I use, of course, the strain of the incident pulse and the strain of the reflected pulse in a time-corrected position.
This one you have the experiment. And actually, the other question, if the chair allows me another question,
Yeah, sure.
is you say you can calibrate with also with the experiment, right?
Right.
But what is not clear to me is the reflected pulse. It depends on the strength measure also from the specimen, right? So it's like you are calibrating, you are assuming you know the properties of the material, right? Because in condition of dynamic equilibrium, then the reflected weight depends on the property of the material.
Yes. Yeah. For if we do not have quite good equilibrium, this I did not check till now. But normally, this I think it does not depend on the material behavior. I just want to know which is. What is interesting for this method is how does this interface behave and how does this interface behave. What is in between? It's for me, let's say, a black box. But I think I need this information.
Okay, thank you. But maybe
Maybe you can talk offline.
Talk offline, yes. Otherwise,
I think it's time to move to the next presentation, and thank you, the kind speaker, for listening. We will invite the next presenter. Can you check if the next presenter is present? The next presenter is here, COSOF D. Complex stress strain analysis for aluminum alloy accounting for damage accumulation. I thought it would be a nice presentation. It's pity the presenter isn't here. Title looks good, right? Can we skip?
One comment. I tried to change rooms a couple times already today, and especially it's a little bit of chaos. So if there is a presenter not present, please do not go on. Just make a break.
No, what is, I think the direction is to continue.
Yeah.
But we will have time. So if we will start the next presentation now, if the presenter comes, we will, of course, we have a time, we will give the opportunity.
Yeah, makes a difference.
But because the instruction to the chairs was,
Okay.
I just missed this one because of that.
Yeah,
He's right.
I cannot. I just missed 3 hours.
I missed this one because
I think we
was
have to talk to the organizers about this. I think the problem is the rooms are scattered everywhere. So there's a high scatter in the data.
Say, if there is schedule, just don't skip. That's my recommendation.
Thank you for the comment here.
Yeah, I missed it because I was timing.
Okay, so we move to the next presentation. We do acknowledge there has been some issue with moving because I'm facing the same issue. I couldn't find this room easily. I should have catch I went to Madrid and I should have catch a plane to Real Paris, not here. It was hard to find here. But anyway, look, thanks for your patience. I think we should move to the next presentation, and if the missing presenters turn up, we will just give the opportunity to present. I think that's the best solution given the time constraints. So our last presentation is virtual, a video presentation. Just hang on a second. It's on precise dynamic disintegration of concrete structures by controlling wave motion.
It's my great pleasure.
So we welcome, I think, Kozi Unesi from University of Tokyo to start the presentation. So anyway, so let's start the presentation then.
Hello everyone. It's my great pleasure to present our recent findings related to the sophisticated dynamic disintegration of concrete structures by controlling wave motion at the 23rd European Conference on Fracture. This is Koji Yanishi at the University of Tokyo. I've been looking forward to attending the conference for a long time, but unfortunately, due to the pandemic, it is still practically difficult to visit the Madeira Island from Japan. So, I am going to deliver a video presentation. We are grateful to Professors Moreira and Reis and the organizing committee of the conference for providing an opportunity to give this video talk on controlled structural disintegration. performed with my co-workers at the Sumitomo Mitsui Construction Company. Thus briefly mention the background. The number of surface and underground structures that are reaching their normal duration of life has been remarkably increasing, and in order to efficiently dismantle such aged structures, either partially for renovation or totally for reconstruction, dynamic technique of blasting by detonating explosives may be employed. Blasting demolition may be accomplished in a very short time span, but it is still planned by experience and may become extremely complex and difficult for reinforced structures that have been constructed very tightly. Hence, blasting tends to be carried out at an